I have to confess that I'm not that young. Maybe I was quite young when I was here first time at CERM. It's 30 years ago, so this whole thing was rather new at that time. So they made it a little bit like Oberwolfach, which existed at that time. And at that time, so 30 years ago, nobody used slides. Everybody used blackboards. So I think if you come after more or less 30 years back here, you must use blackboards. So I prepared my slides on the blackboard now, somehow. So I will start with the title. And the title should appear here. Let's see whether techniques work. You see the title already? It's like slides or like overlays. So you see here, I just pull out. So that's my talk. Yeah? So the title is Regular Language are Church-Rosser congruential. I will explain to you what it means. It's a joint work with Manfred Kufleitner, Klaus Reinhardt, and Tobias Walter. It's very old work. It's appeared at ICALP 2012. And it was based on another work with Pascal Weil, who is present here, which we did 2011, but it appeared 2012. And we concerned with a conjecture here, which maybe some of you know. Ceci n'est pas une frontière de la reconnaissabilité. So it means here. And Arthur, I saw the T-shirt of Arthur, so I had the idea to put this here. Anyway, so let's start here. You will know the standard notions from formal languages. So everything is in context-sensitive languages, and there we have context-free languages, we have deterministic context-free languages, and we have regular languages. Oh, that's well known. Now, inside this class, you have these languages which can you expect, say, in d time O of n, which are here. Some of them have this time complexity, and it's known that the deterministic context-free languages have this time complexity, okay? And of course, regular languages as well. And it was a time of rewriting, word rewriting, and one was interested in syntactic conditions on rewriting systems which give you the same time complexity. And this led to the notion of Church-Rosser congruential languages. This is abbreviated like this here. So everything which is Church-Rosser congruential language has time complexity O of n. That was the interest to introduce it. And you see these languages fall apart with deterministic context-free languages. So the authors from the very beginning, they introduced a more technical notion, but it's not nice. Just to include it like this. They made something like this. So they had if you drop the L, actually, then they call Church-Rosser languages, or C, congruential languages. The L, then you get this, but it's technical notion, I will not speak about it. And the conjecture to prove that this is a robust class was from the very beginning that all the regular languages should be included here, actually. So this part should be empty. I don't know whether it's large or big, but this we can put completely here. So everything is here. So all the regular languages are sitting inside. That's the title. Regular languages are Church-Rosser congruential. Now we must disguise who RM is. So it's here. So first, we use the notion of Church-Rosser systems. And you see that's really old notion, all these old names like Church and Rosser and Thue come in. So we start with a rewriting system. So we are in word rewriting. I'm interested only in finite rewriting systems. So that's part of my condition. So it's a Church-Rosser semi-Thue system. If it's finite and all rules, LR of the system, are length reducing, okay? It means the left-hand side is always longer than the right-hand side. And this guarantees termination, obvious. And termination in linear time, linear steps. And third condition is that the system S is confluent. So it's confluent systems. And what does it mean, confluence? I put here. So I assume you know it. The condition is this one. The system is called confluent. If you look at all these diagrams that you can derive in different directions, it should be confluent. So we must fill the existent part. So what does it say? It says there's a W and we can go down here. Yeah. That's the confluent part. And what is the interest in this system is if you have such a system, you can decide or compute the unique reducible normal form in linear time. Oh, that's the idea. That's the whole idea of the thing. And some more notation. So now we are interested in congruence classes or the symmetric relation. So this means derivation, just as you would apply to grammars. And here we do it in both sides. Yeah? So we're allowed to go forward and backward. And then we get a congruence. And we denote the congruence classes like this. And since this is a congruence, we can look at the classes. And they form a monoid. And what is this monoid here? That's a set of classes with a usual concatenation. So as a set, it's just this. So that's a monoid. Yeah? And somewhere is my definition, probably it's here. What does it mean to be, oops. Goes high enough, I think. So the RM is here Robert McNaughton, Narendran and Otto. They published a paper in the Journal of the JACM, 1988, and they introduced these notions, and in particular they said a language is Church-Rosser congruential language. It's a Church-Rosser congruential language if you have such a nice system, and we can write down L as a finite union of classes. Yeah? And how is now the algorithm to decide the word problem in linear time for L? You start, it means you want to test this here. This congruence, you start with 2 words, you compute the irreducible normal forms, and since this is a finite set here, you have a table, finite table, and you look whether they agree in the finite table. Oh. So that's what you do. Okay. And the word problem for L. So, I mean, you start with 1 word, sorry. You start with 1 word, you compute the irreducible normal form, you decide whether it's in the finite table. Oh, that's what you do. And the important thing is the monoid itself here, this one, it's not necessary that it is finite. It could be an infinite monoid. No? For example, you could recognize this way the language A to the n, B to the n. No? So non-regular languages. Okay, and they looked at this, and they want, as I said, I think the main interest in this conjecture was to show that they have a robust class. Yeah? So it's not artificial, and if you think about it, if it's not artificial, then at least something such simple like regular language should be in sight. Yeah? They knew that they cannot capture all of the deterministic context-free language, so the hope was at least our regular languages should be in sight. Yeah? So this was stated 1988, and the solution was given in our ICALP paper 2012, and now the question is, why did it so long time to work on this? The first thing is you can say nobody was interested. So that's possible, I don't know. But nevertheless, there was some early work. And this work of McNaughton, Narendran and Otto got some attention. And people really tried to solve it. And maybe I will comment a little bit about my personal viewpoint, why the other failed to solve it and why we, ordinary people, came up with a solution. So some more history, which is hidden here. So what was the natural approach to this? It's called early work here. It was around Otto, but not only. So people like Waldmann and Johannes Waldmann, I think, Gödel and Niemann, and some other. They tried to attack this problem for very simple cases. So I would give it to a student like Gödel and Niemann was, you would ask, solve it for simple cases. So what's a simple regular language? And they were thinking, if the syntactic monoid is as small as possible, okay? Z over 2Z, Z over 3Z, maybe finite cyclic groups. And they really worked hard, produced papers and whole PhD thesis on these things. And with enormous amount of technique, they solved essentially nothing. And why? Because it turns out that these are the hardest cases. So first mistake, they tried to attack something which is actually very hard. So we can solve it. And the problem is if A is large, the alphabet is large. And you can imagine then many things must commute. AB is equal to BA and something. Yeah? But if you have length reducing rules, it's not good if AB is equal to BA. Because you must go to something down, smaller. And that's, so somehow they thought they attacked the most difficult problem and they attacked the worst case, somehow. Yeah? Now our result tells us that's okay for all these things. I think they solved it here for this monoid, for arbitrary large alphabet, which was hard. I don't think they had any good results here. Maybe Manfred knows better. Ourselves, we failed to construct a system effectively. If we have 4 letters or 5, 3 letters we managed. 3 letters we managed, so 3 generators, then we managed to give a system. So, but 4 or 5, we know it exists, but we couldn't write it down, or we had no. Okay. So, but then history goes on, and then there were Klaus Reinhardt and Reinhardt and Therien. And they are brave persons. So they announced the result. We can attack all these simple cases. Actually, we know that if the syntactic monoid of the language is a group, that's G, all these languages are inside. That's what they did. The problem with this was it was an unfinished manuscript and it had gaps. Klaus Reinhardt is known to some of you, at least the name, and maybe you can think it's not that unusual for his manuscripts. But if you know Klaus Reinhardt as well, you know that somehow he's always right. So he doesn't. So it's my former student. So I he did this with patronets, and people in the audience know a little bit the story. So I was sure when I heard it that there's something in. And then we came to Singapore, which is a nice town, not only for Formula One. And so I met Klaus actually in Singapore, and he told me that he's still working on this problem. And he wanted to do something with H classes and very complicated stuff. And I said, oh, I don't know, let's see. And I came back from Singapore, and Pascal might remember, and Manfred, they were working together. And I said, I met Klaus, and he had such a nice problem. So if we want to solve it, we should look at aperiodic monoids first. So we did the aperiodics. And then I said, then it's easy. Then we combine the 2 results, and we are done. And somehow it turned out to be true. Somehow it didn't turn out to be true. But the whole thing is really difficult somehow. So I cannot explain it to you here. It's very technical. And the most technical part is in the group case. And not even in this case of Klaus Reinhardt, we had to use a much more general result than they proved in the original manuscript. So we had to redo the proof somehow, to generalize the proof and the statement. So I cannot speak on this, but my idea is, if I'm not too slow, to give you the full proof, so to say, from this result. when we started to work on this, this was not so far away. So we got it rather easily, or at least fast. And then it took us quite more work to get the whole result. Actually, the whole thing was that we got Klaus Reinhardt into the boat to explain us his ideas he had in mind when he used this manuscript. So that was later. So why I was confident to this, because I thought, actually I told Klaus at that time, I think I know the method, what we have to do. So I had a roadmap. So my roadmap is, we had two things inside. So the first thing, I said, let's do local divisors. This I told Klaus already in Singapore, but he didn't really believe in that, I think. So I will explain what it is. And I was confident that it could work somehow, and I will explain to you in a second what work. But maybe even more important was that we did another principle, which we had also here, actually in the first talks, you remember. It's this kind of loading induction. So what do I mean by loading induction? I mean they attacked the wrong problem somehow. They tried to solve a statement which was too weak. And since everything works on induction, if you have a thing which is too weak, it cannot work. You must find the right statement. So what is the right statement? First of all, we make the class of Church-Rosser languages smaller. Let's make it smaller. I think this notion was already introduced by Niemann. I think it's strong Church-Rosser congruential languages. So obviously it's inside here. And the definition is here that we want that the monoid of the Church-Rosser system itself is finite. Not only the number of classes, the whole monoid should be finite. So we add the condition that this monoid, which is defined by the system, is finite. So that's much better, because then we automatically get that all these languages are regular. So this automatically says these languages are regular. So the theorem actually should be that the regular is the same thing as this one. And the proof, what we have to prove is we show that the regular language have this property. Okay? That's the first thing. The second thing is we use a purely algebraic statement. So what is the algebraic statement which is behind here? It speaks about morphisms or homomorphism. So it can be stated like this. And as in the first lectures, I use alpha for homomorphisms. So it says as follows. So for all homomorphisms to a finite monoid, M, which is finite, it could be the syntactic monoid of a language, but in this setting it's in any morphism. There exists a system S, so which I abbreviate like this here, strongly Church-Rosser semi-Thue system, so it has all the properties I listed somewhere here, plus the addition that the quotient monoid is finite, and I want a factorization. So we draw a commutative diagram like this. We go down here with alpha to M, and then we go here. That's a canonical thing. So there's only one choice, which is canonical. It sends a word U to its class. And you get here a commutative diagram. And the morphism is defined by alpha, of course, but we can call it maybe psi. Okay? So that's the statement. The last ingredient on what we have to do by loading induction, I will tell you at the end. Yeah? So I start the proof as I want to do something with length reducing systems. And if you pay attention and if you are interested, you will see I make a mistake. Huh? At the end, I will hide a mistake. And that's the solution, what I mean by here. Okay, I come to this back later. Now I must explain to you what is a local divisor. So a local divisor is as follows. We start with a monoid M, which can be finite or infinite, but it's of interest. It is only the finite case. We take an element C, which is in the monoid, and it should not be invertible. So, one, sorry. We start with an element here, and the one should not be, so it's not invertible, this element. So all non-trivial elements in aperiodic monoids satisfy this. And then we look at the following set, exactly at this set. Maybe I write it now in the, I changed the thing, I prefer. I think it's better visible like this. So under this condition, this M prime here is has less elements than M, because 1 is not in. It is a semigroup, but it has a problem, it's not a monoid. And if you add a 1 to get a monoid, then you have the same size as before, and you're lost. So we make this one here to a monoid. So we multiply like this. Every element can be written like this. It ends with a C. Every element can be written with a C in front. And you multiply in the obvious way. You forget one C. And if you look at this, at least when I came up and I wrote down this equation, I didn't believe that this could work. I thought this is too crazy, it cannot work. But it works. And so that's the monoid. And we denote it by MC. So this is this monoid M prime, this concatenation, and C becomes a neutral element, as you see. C times C is C. Now it's really a divisor, and this is an observation of Daniel Kirsten, actually. Somebody asked me about Daniel Kirsten, so I thought I should name him. Daniel Kirsten, who was in Paris for some time. And we look at those Z. Maybe I prefer on the left. It's not important here, just to see that this is a submonoid here, hopefully one is inside, and it maps to this MC by Z goes to C, Z. And this shows it's a divisor. So in particular, it's aperiodic if the first is aperiodic. When I started to do it, I calculated it directly that this is aperiodic, but it's a divisor actually. So, okay. Now I should move to the proof, or? So you understand this concept a little bit? So the idea is to do induction, and you will see a similarity also to what in the talk of Mark was in the first day, when you mentioned this Wilke proof. You will see there's something similar, and actually I came up with this notion when I was together with Jean-Eric. We were in the habilitation committee of Thomas, and Thomas was using transformation semigroups, and the whole idea was I didn't like it because it was not nice in the sense that it somehow moved from monoids to transformation semigroups, and I thought, oh, that's representation. Why don't we do it here? And so there's some similarity, and then I was asking, did anybody else before me this? And yes, it's a very old concept. It's due to 1872. It's in the hidden manuscript of Karl Mayberg, but he used it for associative algebras. And apparently the semigroup theory community, people didn't use it, maybe also because the transformation thing was already there. So anyway, so we do this now. And for some time, we were quite successful using this induction. And the way why it's good for induction, because you have two parameters again. You have the monoid, which is the main size, and we have some alphabet, which we can make. So we make one big step, making the monoid smaller, and this we let the alphabet be much larger, so we have many tiny steps on the alphabet. And then again, one big step on the monoid. And this makes every induction step very simple. That's the whole idea. Yeah? So let's see how it's going on. Now I come to the proof of the paper for aperiodic. Yeah? And then if time, 15 minutes, I think, should be good. If time, maybe I comment a little bit on the group case. Okay. So the setting is this. Let's repeat. We have an arbitrary homomorphism from some A star, free monoid, to M. M is a finite monoid. We start here, we want to factorize it through the system. It means the congruence classes have all the same images, and this immediately gives a saturation property for the L, if this is a syntactic monoid of M. Yeah? So then this saturates the saturation property. So we want to prove this. And you see, of course, we have two parameters on induction. We have M, which is good, and we have A, which is also good. So we have two parameters we can play on, and this is what we do. So if we are not in the group, and the group case is a base case solved by or announced by Klaus Reinhardt and Therien. So we take this as an induction step, as induction base, and now we do not have a group. And if you don't have a group, then this means that some element, alpha, goes to some element which is not invertible. Okay? Yeah? In the aperiodic case, it's even simpler. We know if M is not 1, then we have this element. So we start with an element. So we may start with an element C, which is a letter, and I use the same letter in C and the image in M, such that alpha of C, which I denote for simplicity by C, is not 1 in M. Yeah? Otherwise, M is trivial monoid, and then we get it, or we're in the group case. So we start with this. The next step is obvious. We do alphabet B. We take C out. That's a small alphabet. So everything is for free for this thing. So we have a restriction beta. So beta is a restriction of alpha to B star. And for free, we get our system with whatever, it's even possible to move this thing. So we know by induction there exists our R, and R is as nice as you like, because it has all the properties we wish. So it is a strongly Church-Rosser semi-Thue system, but it's over B. Yeah. So in particular, because we loaded the induction, we know that the set of irreducible words is already finite. So we know, this implies that the irreducible words, so which cannot be reduced any further, they are in one-to-one correspondence with a quotient monoid. So that's a finite set. So that's finite. And we get a prefix code. So this is we add the C here. See, there's a C at the end. So and that's also nice that we have a code. Now we have a coding. And the next step is we use a homomorphism from K star, which is a finite alphabet, but imagine this K could be large, huge. I mean, it's just huge. Yeah? So we did the big step in deduction we did here, somehow. This is a tiny step here, but here we have huge alphabet, so we must go down on the monoid, and the choice is our local divisor. So we define gamma, which is from K star to our monoid MC. So what do we do? So there's now a little bit tricky. Look at this UC. We have two interpretations of UC. We can think it's enough to define it on letters. Letters are just irreducible words. Yeah? Or we can think, that's the whole word which ends with C, which is in K star. K star is subset, so we can think. So we have two interpretations over K star. We have K star, it's a free monoid. On the same side, it's of course a subset of A star. If you wish A star C. Okay? So first we define it on letters. So this is a reducible word. And we map it to CUC. CUC. And now the magic of this multiplication comes in. That if you multiply it, because we forget one C here, somehow it's written, forget one C, it's a homomorphism, and it's the same on words. Because you see the C in the middle, it's disturbing, but it's always eaten up. So it's a homomorphism. And the monoid is smaller, so we get everything for free. So we get everything for free. What do we get for free? We get our system T, so by induction. So this is big step induction. We get a system T which is strongly Church-Rosser semi-Thue system. By the way, this is a statement which will turn out to be wrong if I do it directly like this. So let's see why. How do rules look like? So if you have an element in here, how does it look like? It looks like something like this. We have some UL, so the L refers somehow to the length of the left-hand side. And the right-hand side goes to some V1, C, VR, you see the L and the R here, of C. And this has all the good properties. Now, the next thing is, we're almost done. That's the funny thing, we're almost done. So we only have to do now, we define our system S, and S does the job. In order to do the job, we must somehow combine both systems, and we must protect the system T from self-overlapping and overlappings. So what we do is, we define our system S as our system R, union, we put a C in front. Oh, I'm sorry, I have a proof in my talk. The first one, I think, or not the first one? Are you hungry for a proof? Pascal, you know it. Let's see. Okay. So this, of course, here, this is in T. So I don't repeat the coordination. Now that's it. Now the question to you. Huh? V, yes, of course, it's V. Yeah, they're very good. But you heard it already, sorry for that. V, of course. Now what is wrong? It's miserably wrong. You see what's wrong? There's no reason why this should be length reducing. Imagine this is length reducing by induction, if we could use it. It's length reducing in the L and the R. But these are words, irreducible words, whatever, in A star. And This is the interpretation in A star, of course. So there's absolutely no reason why the right-hand side should be shorter than the left-hand side. Okay? So the proof fails. Everything failed. So what can we do next? So the proof is wrong. You see it, why it's wrong? There's no reason why the right-hand side should be shorter. These are long words. And they, over the interpretation, over the prefix code, they were length reducing if you could use it in the induction, but they came all up the way by induction. So anyway, even the statement here is wrong in this sentence. So we must do loading induction. So that's the main point. To concentrate on length reducing system was somehow the main mistake, I would say. So when we did in the aperiodic case, and this was our first solution, we did subvert reducing. So we proved much stronger statement. So we defined a system S, which is confluent. And in particular, you can think of it as a subvert reducing. So subvert in the sense of scattered subverts. Reducing for it's a little bit wrong to write down, but shall I write it down? So we can have a subvert. So the right-hand side appears as a subvert of the left-hand side. So formally, it's probably like this: U0, R1, U1, RK, UK, and the R is just the product. So if you think of this, then so that's scattered subvert reducing. Subvert reducing implies length reducing. You can say now they could be L could be equal to R, but it's not important for confluence. And then everything works. You see, if this system here is subvert reducing, it means that the words here appear somehow on the left-hand side. So the same happens here. So everything is fine. So we are done with aperiodic case just by switching the idea that I mean, this is a history of the proof. We came to this step, and then we saw, we are lost here, so we must do something, and then we came with this notion, first notion. Now, in the last 5 minutes, I can tell you why this, again, we couldn't use it for the group case. So now, in order to solve the whole thing, to do the whole thing for all monoids, we would need that our induction base, the group case, has such a system. And actually, we believe it doesn't have. And it's not true that if the syntactic monoid is a group, that we find a system which is subvert reducing. So at that point, that's why we restricted ourselves to aperiodics in the paper with Pascal. We exactly here, we knew this didn't work, and we didn't understand so well the group case. So for the group case, we had to do something slightly different. And where is my, there. In Stuttgart, I can use them simultaneously. It's one more concept, but it's easy to understand. And actually, it's not that difficult to, once you have the idea that this might work, we speak length is a special case of weights. What is a weight? A weight is a mapping weight, say omega, is a mapping from A to positive integers. It's extended to a homomorphism A star, and you speak about weight reducing if the left-hand side has a higher weight than the right-hand side. Okay? You understand this? Weight reducing. And it has the same properties. If it's weight reducing, you can compute normal forms in linear time. So it's the same thing, which is good. But we have to be careful with quantification. We need a stronger statement than here in the sense that we start our theorem. You see, it starts for all m here. Yeah? Okay, for all m. And now we must do a last thing here. We must start our statement, our theorem should start like this. It should say for all alpha and another for all quantification and for all weights. And then exists. So weight reducing blah, blah, blah. Huh? And this does the job, if you can prove it, because if you look at the induction again, it's now hidden, it's up there. The weight, why do we need for all weights? So we have some weight on the K, and we transfer it back to the weight on A star. Or no, the other way around. We have a weight on A, and we must give a weight for K star. Yeah? So the weight on these irreducible words is inherited from the weights of A, the alphabet A, yeah? Because they're irreducible words. They have higher weights, and we must use induction there, so we cannot control the weight throughout. And that's why it doesn't work for length-reducing system. Huh? We must change the weights. And then, of course, the hard part, or most technical part of the paper was to prove that this statement here is true for groups. Huh? And that's difficult, or at least it's technical. And you couldn't use anything, say, you had to do things from scratch again. And that's that's a longer part of the paper, actually, to prove this is true for groups, if the syntactic monoid is a group. But otherwise, once you have done it, then the machinery runs and it gives you the result. Huh? And although you were not hungry for a proof, you had to digest it, and I finished. Okay, thank you.